with okay, testing strong field gravity with quasi-normal modes. Okay, wait. Yeah. So the system we are looking at is we have two black holes that are slowly spiraling around each other and will merge to form a distorted black hole. And this distorted black hole then sort of radiates more energy and forms a stable curved black hole. So this is the astrophysical event that we are looking at. And the signal that we observe in gravitational wave detector data is something that something similar to the one that we show that has been shown in this figure at the bottom. So you have a long in spiral, which corresponds to the signal with increasing frequency and amplitude, and eventually there is a plunge and merger phase where the black holes ram into each other and form a distorted black hole, which corresponds to somewhere close to the peak of the waveform. And then there is the ring down phase where the distorted black hole formed by merging two black holes settles down to its final state. So that's the end of it, which is shown at the very end of this waveform. This data, for instance, corresponds to the first gravitational wave detection that LIGO collaboration did. So in tune with most of the talks in the morning session, in the earlier session, this talk is going to be about testing gravity, but more from an observational point of view. The theory of general relativity is the current state of art description of gravity, but we have not yet tested it in many interesting regimes. Some of the prominent among them are cosmological length scale, strong field regime, regime of nonlinear dynamics, horizon scale physics, and quantum length scales. And gravitational waves coming from compact binary coalescence allows us to probe gravity in few of these non-trivial and interesting regimes. So in this talk, I will be talking mostly about testing strong field gravity. And I will be talking about null tests of gravity in sense that we figure out from theory what is the expected behavior of gravity in a curved spacetime, and we try to extract these informations from imprints present in the gravitational wave observation to validate or prove otherwise against GR. So the part of the waveform that we'll be very interested in is the merger and ring down, the part in which the two black holes sort of ram into each other to form a distorted black hole, and the part in which this distorted black hole rings and settles down to form a final stable state. So we are interested in the last part of the gravitational wave signal coming from a binary black hole coalescence. So the merger part, when the two black holes are just merging, is dictated by the nonlinear dynamics of strong field gravity, because we are still close to the black hole in sense that you're looking at dynamics that are happening few times the event horizon scale. So you're in a strong field gravity regime, and during merger, you also expect all the nonlinearities to play in, which is why you use a numerical relativity setup to compute the waveforms. Contrary to this, when you look at the ring down, this is more of a linear dynamics in sense that this can be explained by linear perturbation theory around the space in the space-time metric of the final black hole that is formed. So in both cases, we are looking at strong gravity. In merger, we are looking at the nonlinear dynamics, and in ring down, you're looking at the linear dynamics. So, so in this talk, I'm going to quickly run through two very famous tests of strong gravity that we do in the gravitational wave community, which is the IMR consistency test and the black hole spectroscopy. So these two are very well-established techniques. And then I'm going to propose a third test that I have been working on for a while now, which is called the merger ring down test. All right. So wait, yeah, perfect. So an IMR consistency test or an in-spiral merger ring-down consistency test, is a test where you try to test whether the dynamics of the gravitational wave, the dynamics of the binary black hole system, is it consistent overall with what is expected to be a GR evolution? So essentially, the way we do this is that there are two independent ways in which you can measure the final mass and final spin of the remnant black hole that is formed. So what we do is we take a waveform, you arbitrarily make a divide between the earlier evolution or the in-spiral evolution and then a post-in-spiral evolution. So in this figure in the bottom, which is a cartoon, the red line divides the pre-in-spiral and the post-in-spiral. And then you use a full in-spiral merger ring down waveform template model, and you try to calculate what should be the final mass and final span of the remnant for each of these parts separately. So you have two independent measures of final mass and final span of the black hole. And then you compare these two and see if they agree. If there is a violation of GR, you would expect or you would hope to find that these two don't agree, but as long as GR is valid, there should be overlapping region between the inference of final mass and final spin from these two separate parts of the waveform. Now, okay, so this is the in-spiral merger ring down test done by the LIGO collaboration for GW15 and 13. So they picked a heuristic frequency of 132 Hertz to divide between the in-spiral and the post-in-spiral. So that's what you see on the left-hand panel. On the right-hand panel, you see the parameter inferences. So the dark purple contour that you see on the final spin, final mass plane is the inference of the final mass and final spin given estimated from the pre-merger or like the in-spiral phase. And then the dot dashed light purple contour is the recovery of final mass and final spin when you use just the post-in-spiral part. And then you see there's a black smaller contour, which is the final mass and final spin found using the entire IMR waveform. So you see that they have a region of overlap. All three of them have a region of overlap, and they contain the region of overlap of the full IMR signal. So this is a good null test of GR. So GR seems to hold in this particular signal and all the signals that we've seen in LIGO. Now, before we go to black hole spectroscopy, we'll take a closer look at the ring down waveforms to quickly go over what's a quasi-normal mode. So the ring down phase, which is the phase when the distorted black hole that is formed just after the merger has radiated away most of its distortedness, and now it's in a state where you can approximate it to be a final black hole with small perturbations on it. And the evolution of this state can be explained via the linear perturbation theory. When your system can be described in this way, you see that the gravitational wave coming from this process can be given as a linear superposition of damped sinusoids. So in this, so you see the plus and the cross polarization in the equations on this slide. And so you have ALM, which will be the quasi-normal mode amplitude of excitation. YLM here is the spheroidal harmonics because you generally decompose the ring downs on a spheroidal harmonic basis function. And the important thing here is to note the tau LM, which is the damping time of quasi-normal modes, and FLM, which is the frequency of the quasi-normal modes. And together, the spectrum of FLM and tau LM is what we call as the quasi-normal mode spectrum. So when we talk about black hole spectroscopy, we mean that we want to recover the frequency and damping time spectrum present in a ring down. So this is the ringdown spectroscopy that was done for GW150914. In this particular event, the ringdown was strong enough only to let us infer one mode, the most dominant mode in the ringdown. So another thing that I forgot to tell this is that in this particular equation, the LM and the LM index mark different modes. So the most dominant mode is L equal to 2, M equal to 2 spheroidal harmonic mode, which which is the most dominant mode. And so essentially we can figure out which modes as well as what frequencies we have in the ringdown. So in this, you only saw the dominant mode, which is L is equal to 2, M is equal to 2 mode. And what you're seeing on this plot is that the x-axis shows the frequencies of the quasi-normal mode, y-axis shows the damping time. And you see multiple contours of different colors, and each of these corresponds to when do you assume that the waveform is describable by linear perturbation theory. So very close to the merger, for instance, when you look at 1 millisecond after the peak of the merger, which is the curve that is indicated in green, you see that you get a different recovery of frequency and decay time compared to when you would assume the ring down to start at 3 milliseconds. And this is expected because there is no absolute way of telling where you transition from a nonlinear regime to a linear regime. And the black curve here is the expected value of frequency and decay time when you use the entire waveform, the entire IMR waveform. So in this test, this is more like a null test in the sense that we see that the black curve is contained within the 3 millisecond and 5 millisecond contours. So we see that the frequency recovered is consistent with what is expected with the full waveform. If we had a stronger signal, a more attractive test would be to try to find out more than 3 independent parameters from the ring down data alone. So instead of having frequency and damping time of just the dominant 2-2 mode, we would like to have frequency and damping time of the dominant mode, plus at least one other higher harmonic mode, which generally happens to be the 3-3 or 2-1, depending on the system. And if you can get more than 3 independent measurements out of the ring down, then we can use something called the Noether theorem, which states that you should be able to describe all the properties of a curved spacetime with just 2 parameters, which we can parameterize as the final mass and final spin. And then there are numerical relativity fits trying to connect quasi-normal mode frequencies with the final mass and final spin. So you can independently estimate final mass and final spin of the object from 2 different methods if you have 3 independent measurements from ringdown. So this is another popular version of black hole spectroscopy that can be done, but our data hasn't been strong enough that we've been able to do this. Then now I move on to a new test that we are trying to work on, and we call it merger ringdown test because it has a very similar spirit to both black hole spectroscopy and IMR test. But the thing that we try to do here is that we ask, so ringdown contains 2 separate pieces of information. You have information of which modes get excited and by how much, and you have which quasi-normal modes get excited and by how much, and you also have information about the frequency and damping time of each of those modes. So the ring down waveform contains these 2 separate pieces of information. And I call them separate pieces of information because the amplitude of excitation and phase depends on the initial condition that's set up for the perturbation, which generally comes from the symmetries that are present in the space-time during the plunge and merger phase. So this part depends on how your binary system was. Was it equal mass system, or was it spinning system, or was it a mass ratio of 5 system? So essentially the initial black hole system sort of affects the quasi-normal mode excitation and amplitude. And then there is the quasi-normal mode frequency and damping time, which is determined completely by just the curved black hole properties, which are the spin and the mass of the black hole, final black hole. But however, within the GR evolution, we can, so as long as GR is the underlying theory of theory, these two are not independent of each other and can be related via a GR evolution. One of the motivation to try to include the amplitude of excitation and the phase into a null test of GR was because merger is a very non-trivial evolution in sense that it does see a non-linearity of black hole spacetime along with strong gravity. Also, it's a very short phase, and one of the idea of this test was to try to increase sensitivity towards the merger phase. And for this, we sort of trade off some sensitivity towards the long in spiral phase, because anyway, an IMR test can take care of it. And then the ring down amplitudes decay exponentially. So further along you go in the ring down, less information you can extract from the ring down. And we wanted to include all of them together, like the amplitude of excitation, phase differences, frequency, and damping time into a test. So essentially, yes, exactly. So then the other thing that we were interested to do was that we wanted to see if we can combine information across multiple ring down observations. So essentially, we wanted to do a stacking, but not of the waveform itself, but of some other statistics that can mark as an indicator of a null test. Also, one very important thing I do want to clear is that this is not to compete with the IMR test or black hole spectroscopy, but this is a test that we are trying to propose to be done alongside the existing test because they ask slightly different questions. So essentially in this test, we'll be asking question of, we'll be checking if the perturbation condition that's set up during the plunge merger phase that is dictated by strong gravity, is it compatible with the ring down properties, as in like the frequency content of the ring down that is dictated by the remnant black hole mass and spin. One of the motivations for this was in an earlier study where we see that if you have black hole ring down with multiple modes that are excited, both the amplitude ratio between the dominant mode of ring down and the subdominant mode is generally very well recovered. Like on the left-hand side, I show you a posterior plot where you see that AR, which is the amplitude ratio between the dominant and the subdominant mode, is recovered really well, and so is the phase. So, and on the left side, you see the difference. So on the left side, you have two different results from two different parameter estimation, the black one corresponding to just a single mode present in the ring down and the green one corresponding to two separate modes. And you see that the amplitude ratio, actually, when you have an amplitude ratio of 0.1, for instance, separates quite well from a single mode. So the ring downs do have a good amount of information about amplitude ratio and phase differences between the modes, which can be harnessed to perform the tests. So what we try to do in this test is like, so this is the ring down waveform. We associate the excitation amplitudes and the phase to the mass ratio. So there are fit formula. So you can fit the numerical relativity simulation to obtain a relationship between amplitude ratio and the initial mass ratio of the system. So of the progenitor binaries, as in like the binary system. So we parameterize amplitude ratios and phase differences in terms of the initial binaries mass ratio. And then we parameterize the tau LM and FLM, the quasi-normal mode frequency and damping time, with the final mass and final spin. So essentially, our waveforms can be parameterized by three parameters, which is the final mass, final spin, and mass ratio of the initial system. However, sorry. Yeah, so and then we perform a parameter estimation using a deep learning setup for all of these three parameters, assuming that these three parameters are independent. Later on, a few slides later, I will come to the point that these three parameters are not really independent, but are related with GR. But for now, I'm just going to talk about the setup for a minute. So we use a deep learning framework. Oh, okay. We use a deep learning framework because we want to combine information from multiple ring down events, and we had to do a large number of parameter estimation. We use this particular architecture, neural network architecture called conditional variational autoencoder. And since I'm running out of time, I think I can skip this slide. So essentially, this is just the details of setting up. Okay. So I just wanted to show very quickly the results of parameter estimation. So you see the blue lines are the injected value of ring down, which is shown on the panel in the right, and you do the parameter estimation and you see that the recovered contours, which are in black, always contain the injected value at within the 90% contours. So essentially, this is just to show how the parameter estimation is working. Okay, so now comes the point that actually the three quantities that we considered as independent when we are doing the parameter estimation, the mass, the spin, and the mass ratio of the binary system, are not really an independent parameters, and they can be related related by expressing the final mass, the final spin of the black hole in terms of the mass ratio of the system. And that is given in this slide. So you can express the final spin of the black hole, of the remnant black hole, in terms of the initial mass ratio, given that your system evolves in accordance to GR relations. Then what we do is, so now we have two values. There is a value of spin that is directly measured from the ring down waveforms. And then there is another inferred spin, which is inferred via the measurement of the mass ratio. So we have two measurements of, so we have two estimates of the final spin. And this particular test of GR would try to compare the measured one with the one that is inferred via the mass ratio. And we assume, so the way we try to combine different information is we try to make a scattered plot. Each point on this graph, on this plot corresponds to one ring down event. And the x-axis is the inferred spin, the y-axis is the measured spin that's directly measured from the ring down. And we try to see the pattern of the scatter. So if GR is valid, then if I can draw a line that passes between these plots in parameterized as given in this equation, just a line. So the spin measured is equal to a plus b times the spin inferred. As long as GR is valid, I should get A is equal to 0 and B is equal to 1, which is what we see in this plot. Then the next question we ask is, how many observations do I need to actually be able to do this test? And what you see is the blue is the value of the median of the recovery of parameter B and parameter A is given in orange. And you see larger the number. So on the x-axis is the number of observation that is used to compute the spread, and the light, like the bands show you the 90%, 1 sigma interval. The 1 sigma interval decreases as 1 over root n as expected in Gaussian noise. So we see that it always has the right value, so the null test is still satisfied. And more the events you have, stronger the test gets. So I'm on my final slide. So this was to demonstrate a proof of concept for a new test of GR that we call as the merger ring down test, inspired by the inspiral merger ring down consistency test. The other important thing about this work was that we tried to use Bayesian deep learning framework to recover all the posteriors, and it seems to work very well. It's really fast in the sense that we can do a parameter estimation in seconds as opposed to days. And this is complementary to the standard IMR test. And we have a few idea of extending these things, especially to things like spinning progenitor binaries, because this work was entirely done assuming that the initial binaries do not spin. We are also working on extending this for supermassive black hole cases that can be detected with LISA. I'm done with my presentation. Thank you.
Thank you very much. Thank you very much for being on time as well and for this nice talk. So we do have time for a few questions. Please, Zakaria.
Hello, thank you for this talk. I have just a question. For example, for two cases, for hairy black holes, if we imagine a violation of Noether theorem, how would you proceed? You would add a new parameter, or everything is based on GR? And the second case, what about non-hairy black holes, but the black holes that will acquire a hair dynamically by accretion or by superradiance or something like that? Yeah. How you will see this excitation of the scalar field if we interpret the scalar field as dark energy, for example.
Okay, so I'm assuming that, okay, I don't know too much about hairy black holes, but I'm assuming that if I'm going to develop scalar hairs or something during merger, I'm going to change the symmetries of how the space-time looks, or the symmetries of the space-time during the plunge merger phase. So I'm guessing that the modes that will be excited or the perturbation condition that I'll be setting up for my ring down will change. So my amplitude ratios between different excitation of quasi-normal mode will change. This means, so this amplitude ratio of excitation directly maps to the mass ratio of the initial binary system. And so the inferred, and this inferred mass ratio will be different from that predicted when GR holds, right? And because the mass ratio is different from when GR, from the case of GR, what will happen is the predicted spin or the inferred spin will change and will possibly not match with the spin that is recovered just using the quasi-normal mode. But there is also this thing that maybe the hairy black holes don't collapse to a black hole, but collapse to some other exotic compact object, in which case you can also maybe see the difference in the measured spin itself. So either way, the point is that it's a null test in the sense that if there is something that's violated, you will see that this test gets a non-trivial answer, which is that you will probably recover a value of A and B that are not 0 and 1. Does that answer your question?
Thank you. And it's the same thing for the second part, for black holes who are in modified gravity and don't have hair and will accrue hair just dynamically.
So, I mean, in modified theory, probably a better thing to look at would be the fact that the quasi-normal mode spectrum itself changes, right? Because the spectrum of a classical black hole, classical GR black hole will not be the same, at least not in all modes, to the modified theory, in which case the inferred, the measured spin itself will change, even though the rest of the dynamic, even the large scale dynamics and stuff sort of might mimic GR, because the final object is not a GR black hole. You're probably going to have, also, it will probably not be defined by just two properties if it's going to be a modification that violates Noether theorem, in which case, again, you will see a difference in the estimated spin and the measured spin of the black holes.
Thank you very much.
Okay, second question by Leila, please.
Hi. My understanding is that the deviation from the ring down
would depend on the sources parameters. So I understand here you're non-spinning, so it would only depend on the masses. Mm-hmm. But I'm wondering, so for your combination that where you use the CVA is a deep learning autoencoder, is it something that you take into account? Because usually the best way to do this is with bias factor combination. So is it something that you do? Is it something that doesn't really matter because you don't care of the spin, but that will be more important when we will include spinning? I would be interested to know.
Okay, so for the so the final spin of the black hole will depend on your initial binaries parameters. In the case of non-spinning black hole, of course, it's just going to be mass ratio. If I include spin, it will change. If I make my initial binary to be spinning, the final spin of the black hole will change because you will also get contributions from the initial spin of the system, and hence the ring down will change. But this is a subleading effect, as in the dominant effect would be similar to the non-spinning one, plus you'll have corrections because you've included the spin, depending on how large the spin is, of course. But the thing is that none of the CVAE formalism that we use require us to have an analytical mapping between initial binary parameters and the final parameters. Like in this situation, we do use an analytical mapping because it is easily available, but we could also just use a tabulated value of different spins and mass ratio to be mapped onto the final spin of the black hole. So it's very easily extendable in that direction, and it's something that we're doing, and it's not how do you say, it's not a real obstacle. It's something that we can do. This test was made more in sense of proof of concept, so we just went to a simpler system, but it can be done, including the spin.
Okay. Okay, thank you very much, Swetha.
Okay, shall I stop sharing?